Wow, welcome everybody. Thanks for coming to our talk. I know that we are the only thing standing between you and lunch. For some of you, happy hour. And so I appreciate you being here. We'll try to keep it interesting and on time. So if you followed Phil or I ever about any of the talks we do, you know we talk about mainframes. We talk about ZOS and mainframes, and this one is no different. But the goal of this talk is really to get you to feel like you maybe actually know something more about this than you think you do. A lot of times the idea of learning this whole new archaic, complicated platform can be a bit much for people to take on. And so we decided to build this talk because there is a component of ZOS that we're going to talk about today that is the Unix subsystem. And a lot of you probably already know a lot more than you think you do about hacking mainframes or testing or security on mainframes because of this subsystem. So I'm Chad Rickensrud. I'm a software security researcher. I work for Broadcom, and I find vulnerabilities in mainframe software. I grew up a 90s hacker kid. Basically what that means is I didn't like authority and people telling me what to do, and I wanted to try to get things that I shouldn't get, all that kind of stuff. Reverse engineering, I like doing this stuff. I've been doing the mainframe side of the house now for a little over 10 years.
So my name's Philip Young. I'm the director of mainframe pen testing at NetSpy. Most people know me by my other name, of Soldier of Fortran. I too was a 90s hacker kid, shocker. I know we look exactly the same. So I'm also a mainframe security enthusiast, and I've been doing this for about 10 years. In fact, we met, this is our 10-year anniversary being on stage together doing a talk.
Oh, I know, yes, I know. Thank you. And that's it. Thanks for coming.
Yeah.
We'd be remiss if we didn't mention one other person. There's 3 people on this slide and 2 people on stage. So Mark Wilson has been doing this a little bit longer than both of us. He couldn't be here today because we didn't invite him, but he really started doing some of this work before we did. And when I started wanting to get into it about 10 plus years ago, the only prior art I found anywhere was Phil's and Mark's. And so just by way of calling it out, because where we were and where we are now is vastly different in terms of the number of people that are into this.
Yeah. So one of the nice things, like I said, we've been doing this for 10 years. So we work closely together. We call each other besties. And I am terrible at code, and Chad is amazing at code. So when I write some code up, I will send it to him and be like, hey, this is crashing. I don't know why. Can you take a look? And then the first thing he instantly does is puts me on blast on Twitter every single time.
Yeah, I mean, if you have Phil write code, I can tell you 2 things. One is it probably will need fixing, and 2, it'll be pretty, right? So you see like all the little ASCII art on the bottom there, that's Phil. It's gonna be gorgeous. I immediately remove all of that and then generally fix it.
All right, take a look at this photo. Tell me where in this picture is the mainframe. Unless you work for companies that have mainframes. No, does someone yell it out? We can't see any of you.
So you have to say
so
loud.
Someone's gonna have to yell it out. We don't have that much time. No, you can just do next slide. Well, that's the mainframe. That part of the room, that's the mainframe. It's the main frame full of CPUs, right? The rest is just input and output, right? The card reader, terminal. Okay, so that was like the original thing. Today, it looks like this. And that huge room-like device now fits all in one rack, right? One rack. And something like this right now is processing billions of dollars worth of transactions somewhere.
Trillions, right? Even.
Yes.
I was just chatting with somebody right before the talk. You know, you are all using this platform, whether you know it or not, whether you like it or not, multiple times throughout your day if you're participating in society in any way, shape, or form. Financial institutions, governments, large retailers, healthcare, airlines, shipping companies, all of these things depend on this platform. The fact that you don't hear about it all the time is really just kind of a kudos to the platform itself because it just works. It runs. It's highly resilient. It's tremendously productive, and it just does what it does. So for the purposes of this talk, I'm going to just mention a couple terminologies here briefly, and we'll get into it more later. RACF is an external security manager. So it is, you can think of it kind of like the Active Directory, right? It controls your authorization, your authentication. If you get a mainframe, if you get ZOS, you don't have to use RACF. There are a couple other commercial ESMs, ACF2 and Top Secret are owned by Broadcom, and RACF is owned by IBM. For the purposes of this talk, we're mostly talking about RACF, but it probably applies to all the other ESMs as well. APF library, the authorized program facility is an operating system control that decides whether or not your process can achieve super user privileges at a CPU level, right? We'll talk more about that later, but just authorized or APF authorization means that your process can elevate its privileges at a CPU level and start doing things like reading and writing memory. Special and operations are system attributes that your user could have within RACF, and if you have those, then your power within the RACF is kind of unlimited. You can pretty much do whatever you want to do. And then the other thing we'll mention by way of terms here is key 0. So all of the memory on the mainframe has a memory key associated with it, and all the processes also have a key associated with them. Generally speaking, you can read and write memory in the same key. So like userland key 8, you can read and write that. There's a special one called key 0, which lets you read and write any memory. So we're telling you these because we're going to start displaying some attack paths along the way, and this will make more sense as we go. This is a slide I used from a talk about 10 years ago when I got into this, and these are the kinds of things that I was regularly told when I said, hey, I want to start applying some of these, who's testing this system, and I want to start applying some of these attacks, looking for some of the same kind of vulnerabilities on this platform that I see in x86, that I see in ARM, and it's not possible. There's magical fairy unicorn juice that keeps that from happening. I don't see this as much anymore. The word is getting out. We're slowly but surely changing minds and hearts about this, but there's still some. There's still some corners of the world who think that this thing is just cannot be hacked. So by way of attack paths, this should look familiar to you. If you do this on another platform, if you do it on mobile or ARM or x86 or whatever, these types of attack paths are not unique to the mainframe. Now, some of the specifics are going to be unique, but the point of this talk is to really tell you that you know more already than you think you do about hacking, security, or pen testing, or whatever on this platform. Network attacks. Network attacks are network attacks. We use TCP/IP, we got web apps, all this kind of stuff on the platform works the same way. File system attacks, right? Insecure data sets and files, same thing as any other platform. Your external security manager, right? Just having things misconfigured or having the security not set up correctly, just like any other platform. And then number 4, which is where we're going to spend most of our time here, ZOS Unix. So you'll hear us refer to the Unix subsystem in ZOS by a couple different names because it's changed names over the years, and in various corners it's still called these different names. Unix System Services, OMVS, or the newest kind of iteration, ZOS Unix, is all referring to a Unix-like interface to ZOS. It's not a container, it's not its own operating system, it is a Unix-like interface to the operating system. And for me, it was very much a gateway drug, right? It was how I got really into it because I felt familiar with this. Like I knew how to operate within Unix, and I was comfortable then learning other concepts about the platform by just starting inside of Unix, right? You've got shells. Now those, you might notice, are not maybe your favorite shells, but there are shells that come with it that you know how to operate within. You've got your hierarchical file system starting at your /root, so you can see things like directory traversal and path manipulation attacks. Your file system permissions work the same way. You've got your 3 sets, 3 octets, read, write, execute bits, just like you know how to do in Linux and Unix. The ESM can provide more security above and beyond this, so that can complicate things a little bit, and it also can make it less secure. How do we access it? Well, if you already have access to like TSO ISPF, the green screen side of the house, you can use OMVS command to get a kind of shell prompt. SSH is the most common, and that's what we'll do here. It's the easiest way. Everybody knows how to use it, and it supports SSH just like you would SSH into any other system. Or, if you know already a lot about MVS and you know how to do JCL and batch processing or whatever, you can build all these kinds of things in scripts and run it that way. We can access data sets from Unix System Services, so we can copy and move data back and forth between MVS data sets. So when you look at this just as an example, just running some random commands in Unix, it should look familiar to you, right? A lot of this you already know how to do, you already know what it means, you know how to navigate it, and we just have to add a few things to your knowledge base in order to get you kind of up to speed. All
right, when we structured this talk, we wanted to, It's really about awareness. We want you to know that these things exist. We also want you to sort of show you how easy it is to kind of hack mainframes. It sounds like you hear about it in movies. So, multiple tools exist today to do things like enumeration, right? This is sort of like the thing that you have to do, the first part of your pen test. And so, we have multiple tools that exist today. So enum is a rec script that runs. A lot of our tooling is going to be written in what's native on the operating system. The newer versions come with Python, but the older versions do not. So you cannot rely on certain scripting languages. So everything we write in Rex, or Java, or shell scripts. OMVS enum is based on lin enum, if you've ever used that before, but it has some other fun stuff mixed in. And then zoshog is, if anyone uses trufflehog, it's the same thing, but for Unix file systems, and we try to find secrets. And the last one is portscan. I'll talk about that in a bit. So all of this tooling is open source, and it's freely available. You can go get it right now if you wanted to, right? That's like, our philosophy is like, we stood on the shoulders of giants. We want other people to stand on our shoulders, right? Like, this should be free and available, and people should be able to use it, right? And so if you've been paying attention, you might have seen a file there called all.jcl in the GitHub repo, right? What this file does, getting files onto the mainframe during my pen tests can be very hard sometimes, right? And you'll see one of the challenges we're going to have in a second. And so it's better if you package everything up before you try to upload a bunch of files. So this JCL will actually upload all of our scripts. It will run them for us. It will do all that stuff, right? Problem is, most mainframes speak EBCDIC. Now, you can upload files to Unix using SCP, right? Or SFTP. But SCP, problem is, if we use SCP, the files are transferred in binary mode, right? It doesn't do any ASCII to EBCDIC translation. And so when we need it to be in EBCDIC. So we got to do the conversion first before we upload the files. Then there's some code page shenanigans going on, so we got to replace some bytes. And then we can finally upload the file. And then once we SSH back in, then we can just run the Unix command submit all.jcl, and it will take care of all of it for you, right? Now, if you're looking at this is how we're going to, for the rest of this talk. If you see the blue prompt, that means we are in Linux. That's our staging area. That's where we're building our tools. If you see this prompt, that means we're on an IBM mainframe, okay? That means we're in the mainframe, we're SSH'd in, we're doing some stuff. Here's enum.rex. This is the rec script that runs. It gathers information in memory, sometimes information that we normally wouldn't have access to, but it's in memory, right? It has a whole bunch of other commands. So here it's going to display the security information. We're going to go into more detail about what it actually found later. OMVS enum is, like I said, it's based on lin enum. It also gathers a lot of information. It's quite noisy, right? Because it's just a shell script. It's written in C shell, because we know that's going to be there. But it's quite noisy. It does all kinds of checks. It'll check your access rights within RecF. It does all kinds of stuff on top of lin enum to help you profile the system from within Unix. The last thing is, what we do during enumeration is we try to break out of the environment. You would be surprised how many times I can go from the mainframe to an AWS instance on multiple ports. I had a client where we did that. We did exactly what I'm about to show you, and they were like, we haven't used that ISP for a decade, right? So that's the kind of fun stuff that we're finding. So you can see here, I run portscan. Portscan was actually written by Owen Henty, a buddy of mine, and I just run egress tester on a different box, and you can see all the ports that get connected in.
So let's go through some of this and talk about what we find after our enumeration of our fictitious system here. Looking at this enum script, a couple things I noticed right off the bat. So first thing, it's going to tell me this is the RecF database and its backup. And also another interesting bit in there is that the KDF AES encryptions are not active. So there's two different ways RecF can store its passwords. One is using a legacy algorithm that's based on DES and MD5. And then there's a newer version of it that uses like AES-256 and multiple iterations and whatnot. They're both, they both can be brute forced using John the Ripper or Hashcat if you get a copy of the database offline. The DES-based one is much faster, and you can do tens of billions of guesses per second, where the KDF AES one will slow you down a little bit. The other thing I want to mention is these scripts are pulling this information out of memory. So there are control blocks, data areas inside memory in every address space on the system that have some of this basic information in it. And it's documented, right? But we've written the scripts to pull that information out of there versus running commands that might generate the same information. And that's because you might not have access to those commands. And if you start running those commands, there's a good chance you're going to start creating log entries and it's going to start looking like somebody's doing something. But if you pull the information directly out of memory, there's no downside to that. So looking at this, just a couple of other things from this script output. Phil's going to talk about this in a minute. We can SU to root without a password. Okay, so what does that mean? We'll hold on to that thought. We see some privileges. If you look at the Unix privileges here, we've got read, write, execute 777, right? So anybody can read or execute or modify these files. You've got a shell script in bin, and you've got an inetd.conf. There's a real-life attack we can do with that. We can do privileged mounts. So this is another attack we can use to escalate our privileges, which I'll talk about in a second. And we can successfully issue this xadder command. So this goes back to APF authorization, and we're going to also dig into this one. But basically, this lets us create APF authorized programs inside of Unix. Then we can build a privilege escalation based on that. If I look at the output from Zoshog, Zoshog is going through your files and looking for passwords or usernames or other kinds of tokens or interesting information. We see this all the time. We see like a db.properties file or something like that might have a username and a password in it, or a Java properties file might have a password in it. And this tool will just go through and find anything that looks like it, and then from that, you can test it and see if it works.
Yeah. So now that we've figured out what is wrong, right? We've done our vulnerability assessment, essentially. Now we need to start demonstrating impact. You would not believe the amount of pushback you get in the mainframe space when you have a finding sometimes. So you have to really demonstrate you did exactly what you did. So the first one, obviously the easiest one, is the stored credentials, right? This is from an example that happened like live during a pen test. Don't store credentials in files. If you have to do that, make sure the permissions are right. Permissions on Unix, like obviously if you run Linux, you're very familiar with permissions, but a lot of the mainframers, they've been doing mainframe for 30, 40 years. They're not as familiar with Unix permissions as we are, right? And so they oftentimes get it wrong. So for example, this was the program, modified for this talk, and you can see right in the file are user credentials for me to use, right? And so when we pull those out, right here, the problem was this file, the owner of the file had chmodded this 777. They had made it world readable, writable, and executable. So that means anyone could read it, right? The script didn't work, and then they changed the permissions, and now it works great, right? So then obviously, look, the easiest thing to do is we just SSH in. Sometimes mainframe hacking is really easy, right? Like everyone thinks it's super hard. This is the easiest thing to do, right? Like it's not that hard. So here you go. I'm going to SSH in. We don't have to like wait for this whole video to finish.
Yeah, like a lot of what we're doing is taking tactics and tools that have worked for years on other platforms and just tweaking them so that they work here.
But here you can see after whoops, I fast forwarded too quickly.
It's okay.
There's another demo that has the exact same thing. I'll talk about it then.
Okay. If we look a little bit into this last one here, we can issue this command. What does that mean? So I'm going to dig just briefly into APF authorization and what that means. And we got to start at the CPU level. So Z architecture is a different CPU, right? It's not x86, it's not Intel, it's not ARM. It's its own CPU for this platform. It has its own instruction set. So there are a number of assembler instructions that are CPU instructions. The majority of those instructions are meant to be able and to be run by any process that's in a like normal state. This is called problem state. There's a reason for that. It's because it's where you solve problems, right? But that's normal operating state. And then there's a small subset of CPU instructions that can only be run at supervisor state, which is like the privileged level. So you can change between those states. Any process can change between those states. The privileged level instructions are the ones where you can change then your memory key and do things like read and write any memory. Mm-hmm. There's an operating system control now, or there's an operating system control that dictates who can make that change, which process can make that change. And most of that on ZOS is done through APF authorization. Now on the green screen side of the house, in MVS ZOS side of the house, that is done with a series of libraries. So there's a list, the APF authorized library list, and a list of libraries, which are like folders for programs, right? So if you have a program in one of those libraries, or if you can add a library you control onto that list, then you can run an authorized program and switch your memory key and all that kind of stuff. In Unix, there's no concept of libraries or whatever. We've just got folders and files and whatever. So those programs get APF authorization by flipping a bit. There's a bit that gets assigned to those programs, and the way you flip that bit is by running this command. So the command is extadder, and then with the +A flag, assigns that APF authorized bit to that program. To be able to run this, you need read or better access to a profile in your ESM that is bpx.fileadder.apf. So when you're doing your enumeration, if you find that you have read access to this, you can probably run this command, and that way you can then build an exploit, APF authorize it, and run it. So what does that look like? So I'll walk you through this. This is an assembler macro, mode set macro, and its sole purpose in life is to switch your process's state between problem and supervisor and back, and key. There's 15 memory keys, 0 to 15, but the special one, the one we're interested in, that's 16 keys. 16 keys between 0 and 15. But the one we're interested in is 0, because 0 has a special capability of being able to read and write any memory. So we want to be able to execute this instruction. The operating system will prevent us from executing this instruction if it hasn't been issued from an APF authorized program. So since we're dealing in Unix, we're going to talk about what that means, and then what would we do? Because just because we can get to the point where we can read and write any memory, that still doesn't give us the ability to take over or do whatever we want to do on the system. We still have the ESM to contend with, right? Because the ESM isn't checking to see if you're in supervisor state. That's a CPU level control, right? But the ESM is checking memory. The ESM is checking memory to see what privileges you have and are you able to do X, Y, and Z. And one of the places it checks these privileges is this data area called an ACEE, which is really just like kind of a cache of your ESM privileges. So when you log in, the system builds this control block in your address space, and it has representations of a lot of the major privileges that you have. And so when you try to do a thing, the system checks this. So one easy way to take advantage of getting key 0 through your APF authorization is to generate another ACEE, tell the system to generate one, and this is a privileged operation. You have to be in supervisor state to be able to do this, but have it generate a new ACEE for some other user that has the privileges you want. So we're spoofing or impersonating that user. So in this case, you can see, I've got Chad and Broadcom, whatever. This is my low privileged ACEE, but because I was able through APF authorization to get to be able to run an exploit, what I can do is I could generate a brand new ACEE for Phil because I know that he has the privileges I want, and then I can just change one little address and point in my address space to the new one that I just built. It's still going to look like me logged in. Everything's still going to, my address space will still be owned under me. But now when the ESM goes to check privileges, it's going to check where this pointer goes to, and it's going to go to this new ACEE that I built. So what does that look like? So this is a snippet of assembler code that kind of shows you that this is fairly easy once you kind of understand what's happening here. So the first thing that happens is we're going to execute this macro. This is the test. If you can get through this, if this works, you're golden. If you can't, if you didn't do the APF authorization correctly or something else is wrong, the program will stop right here. You'll get an 047, and that will be the end of your program. If you get past this instruction, then everything else that happens here, you're golden. The next thing we're going to do is we're going to generate this ACEE using a rackf macro called rackroute, and we're going to generate it. We basically pass it a few parameters, but the main parameter we're passing it is literally just a username. So down below, you'll see I've got Phil as my username there. So it's going to generate, as if Phil logged in, this new data area, and then I will go through the trouble of repointing my pointer to the one that I just created. So how do we build this up? So we write this assembly code in a text file in Unix. We assemble it. This might look familiar because these commands are very similar to commands you would use if you were doing this in Linux or Unix, right? We assemble it, we link it, and then we run that one special step here where we APF authorize it. If that works, you're golden, right? If you can run that last command without any errors popping up, then you've APF authorized it. So the next thing you would do then, if you wanted to use those permissions, like so I've become Phil, and at least for purposes of my privileges. So Phil keeps all his secrets in this one file called secret.txt because he's good like that. So I'm going to run my exploit. And for purposes of security, I will become Phil. You can see that effective user ID when I did an ID. So now the system will treat my privileges as if I'm Phil, and I can go in and see what kind of secrets that Phil keeps in his secret file. Aw, thanks, Phil.
Love you, buddy. All right. You've probably seen this one previous already, right? You've saw, oh, you can sudo root. What does that mean? I understand that. So technically, in a Linux environment, this would be game over, right? Like you've taken ownership of the entire box. On the mainframe, you're almost there. You're so close, but all you really can do is manipulate the Unix file system, right? Because what happens is your address space in memory, that ACE, all that stuff, that doesn't change. Only your Unix UID changes as you're doing commands. So what does that look like in practice? So here you can see I'm Phil. I type the ID command here, right? Very normal Unix-y commands. I type su, so I don't have to provide a password because we're part of that. We have access to that profile. I type ID. You can see I am a different user, like in the Unix system, right? But when I go to run the TSO command list user, it's LU. Every command is an acronym on here, so it's list user. When I type the list user command, it still says that I'm Phil Young. So yes, I might be UID 0, I might be super user, but if I try to do anything outside of Unix, it's still just Phil doing those things, right? So why don't we just do the SSH thing again? That's the easiest thing to do. Just find a user you know is an admin, and then create an SSH key that you can make. So that's what we're going to do. So we're just going to sudo root. We're going to see they don't have an SSH folder, so we just make one. We also then make unauthorized keys file. We chown it. We give it the right permissions. We put our public key in there, and then we're ready to go. And then on the Linux side, we just SSH in. And this is what I was trying to show in the last demo, but thankfully it's here as well. If you look, so now we're running as Mark. So now we're logged in. And Mark has what's called attributes special and operations. You heard Chad talk about that much earlier in the talk. At this point, it is game over. Like we can do anything we want with this account now, right? So usually what we're doing when we're doing pen tests is we're targeting either users who have this or APF authorization.
And it's going to look like Mark did it, right?
Yep.
Because we're operating under his ID. Let's talk about this mount idea for a second. So if you think about any time you've operated on a Linux system, you understand somewhat at least probably the idea of mount points, right? You might have multiple hard drives, and each of those hard drives has a partition, and then those partitions get formatted, and then you mount them at a certain point, right? Like you've got a mount point at /boot and at /root, and maybe another one at /user or var or whatever, and they're partitions on a hard drive. So the Unix System Services works very similarly, but instead of using hard drives and hard drive partitions, it's actually a ZOS dataset that kind of acts like that partition. So you create a dataset in ZOS, you format it, and then you can mount that dataset to a mount point, and that's how you get different mount points for capacity or products or whatever you have. Well, the APF authorization for those programs is stored inside that dataset, is a bit. It's not stored in ESM, it's stored as a bit inside those datasets. So here is the attack. If we have the ability to do what's called a privileged mount, meaning we have the ability to mount one of these file systems in a privileged way. So there's a non-privileged mount and a privileged mount. Non-privileged means you can mount it and still look at everything in there, but the system won't honor any set UID or APF authorization bits that are set. Regardless if they're set, the system just won't honor it. So that's a lower level. If you have this higher level of secure mount privilege, meaning you have update access to one of those two profiles, or you can SU or somehow get to super user ID 0, which also has this privilege by definition, then you can do a privileged mount. So what does this attack look like? The attack looks like this. So I would go back to my lab and I would build the exploits that I want to have on a small ZFS file system on my lab, and then I would create the programs. I'd APF authorize, set UID them, unmount them, package them up, carry them with me, go to the target system, the client system, whatever I'm testing, upload it to their system, receive it and mount it, and then run the tools. And the system will happily run those tools with APF authorization that I APF authorized on a completely different system, right? So if you can run all these commands manually, but this is just showing you in JCL. It's fairly straightforward. Once you get the data set restored, it'll take you more time to figure out how to get the data set offloaded, back, uploaded, on, restored than it would then once you run the mount, one command mount, and then you point it at the OMVS directory that we created, go out there and I'll look at it and make sure it mounted okay. You'll notice a couple of things about this when I list it. First of all, I'm using a capital E switch. That capital E switch doesn't exist in Linux. Here, it means show me the extended attributes. So down in the, you'll see between the normal octets and the owner, there's some other bits there. That A, if that A shows up, that means it's an APF authorized program. You'll also see in the previous one, it's owned by UID 0, and you've got the set UID bit set there as well, so that program will run as UID 0. And then we run those, and the system will happily give us run those exploits as APF authorized, even though we built them on a completely different system.
Yeah, he makes it sound so easy, huh? Alrighty, so let's talk about buffer overflows for a bit. So, lots of Unix programs are written in C, a non-memory safe language, right? And for a long time, it was theorized that you couldn't do buffer overflows on mainframes until someone proved them wrong. So, not me, they're right here. So basically, it's just like any other Linux environment. You have C programs and you can do buffer overflows. But if the program is APF authorized, then we can do the exact same exploits we've been talking about this whole time. How do we find APF authorized data sets? Very easy with this simple find command. That's it. The extra attribute A finds all of the data sets that are APF authorized.
All the programs.
All the programs that are APF authorized. So this is one screenshot of it scrolled for a long time, right? And this is on my lab system where I don't have any vendor products or anything installed. Now look, we've only got 8 minutes left. I do not have the time to get in depth into mainframe buffer overflows. There's just not enough time. Thankfully, you don't have to worry about it. Other people have already done the research and have given talks about it. So Jake LaBelle, who really is the godfather of mainframe buffer overflows, gave a talk at DEF CON 2 years ago. Chad gave a talk at DEF CON 10 years ago talking about mainframe buffer overflows. And then Jake and I also gave a workshop, which is freely available on GitHub, where you can learn how to write mainframe buffer overflows, right? Now, you learn how to write a buffer overflow, then once you find an overflowable buffer in an APF authorized program, it's just about putting some shellcode together and exploiting the buffer. That's all it really takes.
So that's just the shellcode from the exploit that I had back in the assembly stuff that I showed you.
All right, let's talk about some honorable mentions because we didn't have time for them all. Improperly using the ESM to manage security, you can actually let it drive the security in the file system, and it will ignore the permission bits and go whatever RACF or whoever says to give that access rights. I was on a file system, the permissions were set correctly, the ESM was not, and I had read access to every single file, including private keys.
This is hard. This will confuse you because it will say oh, I should have read access to this file, but if they have some certain features turned on in the ESM supersedes those permissions, and so you might be looking at something like this is 777, but I can't read it. What's going on? That's your clue that maybe they've turned on some of those ESM permissions to override what's in the file system. It won't reflect it back to you. So it could go either way. It could be more restrictive, and in some cases, like Phil said, it could be less restrictive.
Yeah. The other one is a world writable file in /bin that was run every time a user logged in. It was a shell script, so I just edited it and easy stuff. It's not super hard. I see this a lot, so I just wanted to talk about it here since I have the stage, but I see lots of temp logs that are world writable on mainframes in Unix, right? Don't do that. Please don't do that. And the last one here is LF5, they still run web apps, right? And we found a vulnerable web app that allowed local file include to files we couldn't access in Unix, right? So all kinds of things that you see here in the Unix side of the fence.
So we'd be remiss, and also I know that IBM's in the audience, so we had to throw this in here. How do we prevent and detect this kind of stuff, right? I mean, ultimately, the goal here for probably most, if not all of you, but at least most of you, is to not have this happen, right? Because I like it when my bank card works. I like it when my airline is on time. I like it when I can buy something online and it shows up 7 minutes later. how do we prevent and detect this kind of stuff? So prevention is a lot of what you think it is probably if you were doing this in a Windows box or a Linux environment, right? Look at those file permissions. I mean, I have scripts I run that just look for world readable files. Same thing you're learning in like pentesting 101 on Linux. Check these. There are other profiles that are important, right? There are classes out there, facility classes, Unix priv classes, serve-off classes. But these particular 3 profiles up here are very dangerous, right? I'm of the mind that none of this should be on anybody's daily driver ID, right? Nobody should have the ability to ask you to root without a password, to do privileged file system mounts, to have all of those file modification attributes that you can get from these on their daily driver ID. That should be a break glass scenario. You just should not need to do that every day. Because the more people that have these permissions, right, that's just a bigger attack surface for us if we want to start spraying passwords or cracking passwords. Looking at your logs, right? I mean, it's basic stuff, right? We get SMS, the system messaging facility will kick out log messages. Look for both successes and failures, because you might have somebody who's already ahead of the game and they're succeeding at this, and you want to know, why are they constantly SUing to root? Why is that working? Why are they constantly APF authorizing a program in OMVS, in Unix System Services? Like, is that something that you would expect them in their job to be doing on a regular basis?
Yeah.
Looking for large numbers of unauthorized attempts on files, right? Somebody scanning the file system will show up like a sore thumb in those logs. You should be looking for that. And of course, thousands of outbound TCP connections, right? Egress filtering is still really, really bad on the system for some reason. The number, Phil's not exaggerating, the number of these systems I found that have a pass for being able to connect directly to systems on the internet, have open SMTP relays on them, right? Nobody, what could happen bad there, right? All of these things exist on these platforms, and you have to look for them, and they're all in the log. Like you can find all of this activity by looking through the logs. And then the last thing is Unix file system auditing.
Yeah, I'll explain what that means. So the nice thing about ZOS Unix is if you pass ls this capital W here, you can see it's now shown us a new field that we get, and it's all Fs, right? So a colleague of mine, David Bryan, and I had to figure this out because we're working on a client to help them improve their monitoring capabilities. So what this means is it's like 2 halves, right? One, you have the user-controlled side. So users can set, if you can chmod the file, you can chaudit the file, right? You can set like I want this file. If people execute it, I want to know. Then you have an admin control side, which the admin can set. This is the default setting. Fail, fail, fail. So that means if you fail to read, execute, or write, it will generate a log. My recommendation is you go and find your privileged files that you really care about and change it so that you can have them be audited for every access attempt, right? So now you see it's all A's, and that means all. So that means success and failures will get logged for read, write, and execute. Now, first I want to do some shout outs because we wouldn't be up here if it wasn't for a bunch of people in the community. So first I want to say thank you to the Mainframe hacker community. You can see there's some screens there from those folks. But when we started, there were 2 mainframe hackers, 3, there were 3. And then Henry joined us, and now we've got like a dozen mainframe hackers.
Or more.
Or more. The Moshix Discord, if you're interested a little bit about this topic, and you think, oh, I want to learn more about mainframes, Moshix has a great YouTube channel, also has a great Discord where you can chat about mainframe stuff, learn about JCL, all that kind of stuff. The mainframe cybersecurity community at Share is great. If you are thinking about Share as like the mainframe industry conference, you can go there, and they are super welcoming. They love having other cybersecurity nerds to talk to about mainframes. It's great.
I'll just throw in also the large companies that deal in this platform.
Yeah.
Especially, and I'll call out IBM. Like they have been very partnering. They partnered well with us through this stuff because ultimately they don't want to see the system get hacked and on the front page of the Wall Street Journal any more than less than anybody does. And so they've worked really well with us over the years, and we get to come up here and say the things that they can't. But it works really well. It works really well, and I appreciate all the support we get from those guys.
Yeah. So this is how you can contact us. If you have any questions.
We're going to go to the wrap-up?
Yes. Apparently we're going to the wrap-up room. So you can ask us your questions there. This is how you can get a hold of us. And we want to thank you for having us come speak with you. Yeah, all right.